Log on, tune in, find out. Another good idea from Cambridge.
So, Dominic and Michal talked almost everything about Lemaître. I shall try to say something. Half the same things from a little bit different angle. Even the pictures are already known to you, but the number of pictures unfortunately is limited. But it's interesting to know that some of them were made by Lemaître himself. He almost always carried with him a little camera and took a lot of pictures. Unfortunately, after his death, the majority of his photographs and his documents and his papers, manuscripts, were destroyed simply. And it was Godard who prevented to be destroyed all of them. So only a couple of pictures have been preserved. Okay, that's all right. So, in 1931, Georges Lemaître published 8 papers. Among them, 2 occupy a special place in the history of cosmology. We already are acquainted with them. These 2 papers, I will come back to them in a moment. This is planned on my talk. It's very simple. In the first part, I will speak about the early work on singularities. As you know already, Lemaître was a very good mathematician and he adored calculation. Although his very frequent saying was that before you come to calculation, you should think very seriously in order not to do perhaps any calculations at all. And I think it was his strategy. And I will show that his greatest ideas also are based on his mathematical work. So then we will deal with this 1927 logarithmic infinity model without the singularity and his road to primeval atom, and at the end Lemaître's cosmology, quantum cosmology. Okay. And now part 1, early work on singularities. In November 1915, a week before Einstein presented to the Berlin Academy of Science the correct form of his gravitational field equations, Einstein considered the perihelion motion of Mercury based on an approximate solution, which later on turned out to be a special case of the correct equations. The correct solution was discovered by Karl Schwarzschild in 1916. In Einstein's approximate solution, 2 non-regular points appeared. One at the beginning of the coordinate system, at r = 0, and another one at that distance from the beginning. And Einstein himself at that time was too busy to be interested, too busy with calculating the motion of Mercury and comparing it with astronomical data. He was very, very great moved by the fact when he discovered the agreement between the calculations and the known data. Later on, he said that he had a kind of heart palpitations. He was so moved by this agreement. And so he was too busy with Mercury to pay any attention to these 2 points. And it was David Hilbert who noticed the problem. As you know, perhaps, there was a sort of competition between Einstein and Hilbert in the last days before the discovery of general relativity. Who will be the first to formulate the correct form of Einstein equations? And in fact, David Hilbert was first by about 3 days. But Einstein was not aware about that because he was so busy with his calculation that he never read letters from Hilbert. And in fact, Hilbert, a few months ago, learned from Einstein, who was in Göttingen and had a lecture about the problem. And he approached the problem from the mathematical point of view, and he was the first, in fact, to discover Einstein's equations, although he did not appreciate fully its physical meaning. And Hilbert noticed that there are two non-regular, this name non-regular comes from Hilbert himself, but strangely enough, a great mathematician did not capture the difference between genuine singularity and the one arising from the inappropriate choice of the coordinate system. It is a sign of the fact that the singularity problem is a very malicious one. From the very beginning, it was involved in many both conceptual and mathematical problems. Einstein was very unhappy with the Schwarzschild solution because it presented a well-defined structure of space-time due to a single body. And in his view, this contradicted Mach's principle. As it's very well known, the ideology which Einstein read of science of mechanics by Mach was a great inspiration for Einstein when he created general relativity. And by Mach's principle, Einstein understood the doctrine that, roughly speaking, space-time should be generated by the distribution, the global distribution of masses in the universe. And the Schwarzschild solution seems to contradict that ideology because it possessed a very well-defined structure, space-time structure, due to a single body. And Einstein believed, after Mach, that if we have the universe with a single body, this single body should have no mass, because the mass is induced to a given body from the distribution of all other masses in the universe. Einstein's dissatisfaction with the Mach's principle problem grew even more when, in 1917, Willem de Sitter, a Dutch mathematician and astronomer, published a new solution to his equations. And the solution represented the empty universe. It was against the Mach's principle. And this anti-Machian situation was not acceptable for Einstein. And Einstein argued, there was a great discussion between Einstein and de Sitter. Several papers were published by both of them. We can admire the speed of publication at that time. It was wartime, 1917. And Einstein, I think, if I remember, published his paper, the first cosmological paper in March. And in May issue, de Sitter already presented his answer to that. Probably, not probably, it's true that de Sitter knew Einstein work from the manuscript Einstein sent probably to him. And Einstein argued against de Sitter's solution that he said that in the coordinates used by de Sitter, there are two non-regular points in the de Sitter solution. Again, at the beginning of the coordinate system and at that distance. And Einstein claimed that the first of these singularities can be removed by the change of coordinates. But the second is truly disastrous for the de Sitter solution, and this solution should be rejected. In this way, Einstein tried to save Mach's principle. As we know today, it's just opposite. Well, and exactly here, Lemaître enters the stage. The first Lemaître published paper, the first in the field of cosmology or general relativity, is this one. Note on the de Sitter universe. It's published in Journal of Mathematics and Physics. This journal was published by Massachusetts Institute of Technology, and as far as I know, it does not exist anymore. In both coordinate systems, those used originally by de Sitter and later on by Eddington, the universe is static and its space is spherical with positive curvature. Lemaître introduced new coordinates in which the universe is non-static, it expands, and space is Euclidean. Here we have a very beautiful picture. Space-time, which is invariant structure, in de Sitter model is this hyperboloid. And in original de Sitter coordinates, this space-time was decomposed into time, which was the axis of symmetry, and perpendicularly spaces, local instantaneous spaces, which were spherical. In Lemaître's coordinates, the space slices are like that. They are Euclidean and go to, in both ways, always to infinity. New coordinates clearly display the homogeneous and isotrophic structure of the de Sitter world, and all its points here are on equal footing, and central singularity disappears. And there is also no mass horizon. The mass horizon was invented by Eddington when he analyzed the de Sitter original solution. He claimed that it's not empty, but at the second singularity there is a kind of accumulation of masses. But as shown in this paper by Lemaître, it is a byproduct of bad choice of coordinates. It is interesting to read Lemaître's comments on his own work. He commented on the non-static character of the de Sitter world and on the zero curvature, or flatness of space in the de Sitter world. Lemaître quotes Eddington, who says that it is sometimes argued against de Sitter world that it becomes non-statical as soon as any matter is inserted in it. But this property is perhaps rather in favor of de Sitter theory than against it. And Lemaître comments that in the following way: our treatment evidences this non-static character of de Sitter world, which gives a possible interpretation of the mean preceding motion of spiral nebula. So it is a first hint that he was interested in this radial motions of nebula. And he says this is rather in favor of de Sitter solution. But the second problem, the zero curvature, is a compromising property of the de Sitter universe. This space is Euclidean, flat, and extends to infinity. And he says this property is completely inadmissible. With this property, we are led back to the Euclidean space and to the impossibility of filling up an infinite space with matter which cannot be finite. De Sitter's solution has to be abandoned, not because it is not static, but because it does not give a finite space without introducing an impossible boundary. So we see how important role prejudices are played in cosmology or in general in science. I remember Weinberg in his 3 minutes, first 3 minutes, wrote a very remarkable sentence that it's no problem not to have prejudices, but the problem is to have correct ones. The idea of a closed universe belongs to Lemaître's deeply rooted philosophical prejudices. Of course, it was suggested to him by first Einstein cosmological work, in which the space was closed, compact. Einstein selected such a topology in order to avoid problems with the boundary conditions in infinity. And this idea influenced a lot of cosmologists at that time. It is interesting that in the first period of general relativity, almost exclusively closed spaces were investigated. In his seminary years, when he studied for the priesthood, as we know from Dominic already, Einstein wrote an essay entitled La physique d'Einstein. In this essay, he expressed the view that the space had to be finite, since otherwise it would be not accessible to the human mind. I think that one can see in this view some traces of his neotomist doctrine, to which young Lemaître was exposed at the University of Louvain. And according to this doctrine, actual infinity is a self-contradictory. Therefore, matter could not be actually infinite. And if space is infinite, then and matter finite, then we would have an inadmissible boundary, and he objected against that. And this was view which Lemaître cherished to the end of his life. For the title of his conference at the Catholic Institute in Paris in 1950, he chose L'univers, problème accessible à la science humaine. The universe, the problem accessible for the human science. And one of the conditions of this accessibility was a finite space. This is well, side remarks, but of course I think very interesting. This is about de Sitter solution, but Lemaître played also an important role in solving the enigma of the Schwarzschild singularities. And the problem was present already in his doctoral thesis presented to the Massachusetts Institute of Technology. We heard from Dominique about that. But later on, and he was never published, but later on in 1933, Lemaître published a very important paper, L'univers en expansion, which never was translated into English, and it is one of the most important cosmological papers by Lemaître. It is pure, almost pure mathematics. There are very nicely elaborated mathematical problems following the early cosmology. At the end, the last section of this paper is about the singularity, and he writes that Einstein suggested to him no, not Einstein, sorry. It is not in the last section. The problem was suggested to him by Eddington. Namely, Eddington noticed that Einstein equations for a homogeneous spherically symmetric perfect fluid was solved by Schwarzschild. It's known today as an interior Schwarzschild solution. And Eddington claimed that the problem could be badly posed since density is not coordinate independent quantity. And Lemaître took over this problem, and he defined invariant quantity composed of density and pressure. This is this quantity. This should be rho and density, and here P for pressure. This comes from the fact that PowerPoint, at least my version, is not device independent. And this is why I decided to omit this accent, French accent over I in Lemaître's name, because various beautiful pictures appear. Okay. So Lemaître defined this invariant quantity in units in which speed of light is equal to 1, and found a solution which, for small densities, approximated the Schwarzschild solution. He then considered, and it was not homogeneous, this solution found by Lemaître. And he then considered the case when the fluid is, well, inhomogeneous, but of constant invariant density, this one, and produced a solution which today is known as Tolman-Bondi solution. Lemaître in this work qualified this newly found solution as probable Mount nouvelle, probably new one. In fact, it was obtained in 1922 by Marcel Brouillard with the help of different methods. And as special cases of this solution, Lemaître obtained Einstein's static universe and De Sitter empty universe. Tony already told us about that. And later on, this suggested to him an idea that there must be a solution which is interpolated among these two solutions. And in this way, he found, he computed all the solutions to Einstein equations now attributed to Friedman. And in the course of this work, Lemaître found a coordinate system in which the singularity at this distance from the beginning, 2m, disappears, and there remains the central singularity as the only real strong curvature singularity in the Schwarzschild solution. In this way, he solved the problem of singularity. And Einstein himself was extremely unhappy with the existence of singularities and had an idea that the appearance of singularities is due to the assumption of the spatial isotropy. And he claimed that if we get rid of the assumption of the isotropy, and when we compress not isotropic configuration of matter, then perhaps can go to the expansion without any singular points. And he discussed this problem with Lemaître and suggested to him a simple anisotropic metric, today known as Bianchi-1 metric, with an advice to him to compute the corresponding work model to see whether they think, and to see just, he believed that singularity will disappear. And this is the last section of this 1933 Lemaître paper. Lemaître confesses in that paper that he had no difficulty in computing this model, but it turned out, strangely enough, that the singularity continues to exist. Even more, it is evident from his calculations that the tendency to produce singularity in that kind of metric is even stronger than in the case of the isotropic distribution structure. And at the end, he comments, Lemaître comments that the above is not a formal proof of the impossibility to avoid zero volume by anisotropy, because the form of the metric which was assumed is not the most general imaginable, but this indicates, after all, in a quite general case, that anisotropy acts in the opposite direction. So he developed an idea that singularities are not easy avoidable in general relativity. What is very interesting, that if we look at the calculations made by Lemaître, we spot a certain inequality which plays an important role in his argument. And this inequality reappeared in the proofs of singularity theorems in the 60s by Hawking, Penrose, and others, and is known as energy conditioning. It is a special case of the energy conditioning used later on in proving singularity theorems. But the important point is that from now on, Lemaître knew that singularities are not easy available in relativistic cosmology. And now part 2, from logarithmic infinity to the primeval atom. This I can be brief because almost all is already known to us. This is a famous paper on 1927. I agree with Dominique that here we have for the first time explanation of redshifts, but I think we have even a little bit more in this paper. Namely, for the first time, Lemaître tried to make comparisons between predictions of his model with actual measurements of redshifts. This is the page from this paper with this empirical data and his calculations. And so it was the first paper in relativistic cosmology in which theory was confronted with observational data. This is which makes this paper historically extremely important. This was 2 years before Hubble discovered his law. This is the picture taken from Hubble's famous book on the real of the nebula with empirical data and his law here. We see that the dispersion of observational data is quite pronounced. And here is a recent diagram, and this little spot here represents all this square here. So we are now much better acquainted with the universe and its structure than many others of biology. Lemaître computed all solutions to Einstein equations. So we have found among papers left by Lemaître a red path, and in this red path there were some hand calculations by Lemaître. They were proofs of his article of 1927, which we saw during the morning lecture. And there was this diagram showing all solutions to Einstein equations with, so to speak, with the ordinary cosmological principle. At that time, this name was not used. It was simply an assumption of isotropic homogeneity. Here we have all Friedman, Lemaître, we can call them solutions. Here we have three classes: curvature, positive curvature of space, zero curvature of space, negative curvature of space. Friedman wrote two papers, 1922 and 1924, and he computed in the first of these papers, he computed all these models with positive curvature of space-time. So he found all these solutions. In 2 years later, he published a paper with negative curvature of space. Strangely enough, he never published, except he used these solutions with flat space. Probably he considered that self-evident. Lemaître, as we discussed with Dominique today, probably starting from his doctoral thesis in Massachusetts Institute of Technology, he knew all these solutions. But in his red path were these solutions, these ones only. And he selected to compare the theory with observational data this model. Let's look at it a bit closer. This is cosmological constant. It has a distinguished value, which is called here lambda E Einstein. This value was adopted by Einstein, and it is necessary to have a static solution here, which never expands or contracts. And this is only valid for the very special choice of the value of cosmological constant. And with this constant, with Einstein value of this constant, but with little bit different initial conditions, we have this asymptotically or logarithmic solution, which has no singularity but expands forever and goes to the decimal empty universe. Why Lemaître decided to choose this model? There was no singularity. At that time, he was not yet aware that the singularity cannot be easily avoided. It was 1927, and he computed that in 1933. So, and the second problem was the problem of the age of the universe. which at that time the observational from the age of from observational data was seems to be much longer than from the expansion of the universe. So it was reasonable to have the model without the image of the singularity. Well, but he was happy with this solution for a short period of time, because we know already the origin of his idea of primeval atom. This is the famous address to the British Association for Advancement of Science by Eddington. We know already the content of that. Lemaître, Eddington said that the universe, space of the universe is closed, but time is open, and if we go back, we go to the beginning of minimum entropy, and this sentence was quoted today a couple of times philosophically, the notion of the beginning of nature is profound. And as we know, Lemaître answered this note. Let's take a look at the title. This is the end of the world from the standpoint of the mathematical physics, and here the title is the beginning of the world from the point of view of quantum theory. So there's a parallel between the titles. And he says that Sir Arthur Eddington states that philosophically the notion of the beginning of the present order of nature is repugnant to him. I would rather be inclined to think that the present state of quantum theory suggests the beginning of the world very different from the present order of nature. Thermodynamical principles from the point of view of quantum theory may be stated as follows. One, the energy of constant total amount is distributed in discrete quanta. Second, the number of distinct quanta is ever increasing. And if we go back in the course of time, we must find fewer and fewer quanta until we find all the energy of the universe packed in a few or even in one unique quanta. This is the primeval atom. So, having an idea of primeval atom, Lemaître had to change his view on the evolution of the universe. And he selected this model. This model also is with the value close to the value of Einsteinian value of cosmological constant. And if lambda is equal to lambda E, then we have a static universe. And if it's a little bit bigger, then we have this quasi-static period in the middle. And if we take a bigger, even bigger value of lambda, then this quasi-static period can be made as long as we wish. And so this gave great flexibility to Lemaître in introducing in concordance with the theory of empirical data as far as the problem of the universe is concerned. And about that, he wrote the following: the radius of space can start from zero. Such a singular event, which arises when space has a zero volume, is a bottom of space-time. This is very often used expression, bottom of space-time, which terminates every line of space-time. We should notice here the following thing. When Lemaître spoke about the primeval atom, as we heard this morning, he usually considered the primeval atom as very small from the cosmological point of view, but never zero. But when he treated the problem from a mathematical point of view, he says about the zero, starting from zero. And in a very modern way, he treats space-time which terminates at every, the space-time singularity terminates every line of space-time. This is a very modern formulation, because today we define mathematically classical singularities as those regions in which all histories of particles and photons, that is to say, space-like, time-like, and zero geodesics terminate. So the space singularity is not a point or place in space-time. It is a kind of edge, a boundary, at which all histories of particles and photons terminate. And we treat that as a criterion whether the space-time is a singular or not. If we can prolong all histories of particles, photons indefinitely, there is no singularity. But with the proviso that prolong, we should understand in a special geometric term. We must speak about geodesic completeness, but I shall not go into details. And if at least one history ends suddenly, then we meet a singularity. So he had a good intuition here. And he was used to say that singularity is a geometric support of primeval. So we see that his work in mathematics inspired him in his thinking about physics, and vice versa. So it was a kind of feedback. And now Lemaître, quantum cosmology. Lemaître was one of the first cosmologists, simply not the first one, who included quantum physics into a cosmological model. It was not yet a quantum gravity theory, but the primeval atom certainly was a quantum object. Well, we know already everything from this morning talks, but perhaps a little bit different angle. In the classical view, the same deterministic laws that are able to predict the future will also be employed to compute more remote conditions from which the initial conditions of the present universe may have evolved. Therefore, it is difficult to understand how the initial conditions could really have been the beginning. We can always choose something which is out of which these initial conditions should evolve. And this is, Lemaître writes, essentially one of Kant's antinomies, the antinomy about the beginning of the universe. And he says such an antinomy is valid as far as we remain in the context of classical physics. But if we go to quantum mechanics, situation it changes drastically. Any physical system, and therefore the universe as well, is described by an assembly of potential states which can be or not to be occupied. And the most probable distribution is that of equal occupation of all possible states. Since the entropy is a measure of the total number of individual energy packets, we may say that the final state is the one with the maximum entropy. And conversely, a state of minimum entropy would be a state in which energy is condensed into a few packets as possible. This state is called the primeval atom and can be regarded as the physical beginning of the universe. So we see that he applied some general principles of quantum mechanics to cosmology. The subsequent evolution is not encoded in this initial state. It is not like in phonograph when everything is encoded in the disk. A classical determinism does not stand anymore. These are almost words of Lemaître. I a little bit abbreviated them. Initial conditions need not have the same degree of freedom as has the universe that has evolved from them. Events progress with energy being split into more and more distinct packets. From the same beginning, very different universes can evolve from the same beginning, various evolutions can follow. When the number of individual pockets becomes very large, the essential indeterminacy ceases to be effective and is gradually replaced by determinism characteristic for macroscopic phenomena. So only when we have a big number of physical units, so to speak, then everything from quantum world is being averaged, and we have classical physics. Standard quantum mechanics, which Lemaître applied to cosmology, does not pose the question of quantizing space-time. This was one of the questions this morning. But at this point, Lemaître goes beyond standard quantum mechanics. And he assumes that space-time and time are intrinsically statistical concepts. Of course, it is also borrowed from thermodynamics. Consequently, we cannot ascribe to them any physical meaning before one has a sufficient number of physical individuals. We should remember that his vision was the following. We have the primeval atom, it splits into fragments. This fragment split into more fragments, and the multiplicity is growing. In his view, space and time emerge from the simple initial state as the process of energy pulverization progresses. And he writes, beginning of multiplicity really means the beginning of the very meaning of any notion which involves a great number of individuals. Space and time are such notions which involve a great number of individuals. It stands just before the beginning of space and time, which acquires progressively a meaning while multiplicity is increasing enough. So in the beginning is atemporal and spatial, because there is no space and no time. Well, it's quite a modern view that on the Planck level there is no time and no space in the current understanding of these terms. He never speaks about quantization of space-time, but in fact it is some presentiment of that here. As space and time are the indispensable tools of any physical notion, it stands just before physics. Physics is born together with space and time. Today we would be inclined to say that we have some physics before space and time. Space and time are not necessary conditions for physics to be all these present theories and theory, good theory. They are looking for physics before we have ordinary space and time. It was, as Lemaître said, a grant for physics. This grant for Lemaître was indeed inaccessible. Today, various models of quantum gravity offer a wide field of speculations concerning the birth of space and time. But we see that at least qualitatively, our present ideas are, well, in some sense, in agreement with Lemaître's view. Very roughly speaking, of course. In modern view, quantum gravity regime should remove the initial singularity from the picture of the universe. This is our hope. For Lemaître, on the other hand, the initial singularity in Friedman's cosmological models gives a natural geometric support for his primeval atom hypothesis. He writes, the radius of space can start from zero, such a singular event which arises when space has zero volume is at the bottom of space-time, which terminates every line of space-time. We already know that. And we may speak of this event, this atemporal event, as of a beginning. I do not say a creation. Physically, it is a beginning in that sense that if something that has happened before, it has no observable influence on the behavior of the universe. This is a quotation from the Japanese encyclopedia paper. We have found with Laurent Godard among papers written by Lemaître, a manuscript, quite an extensive manuscript, I think about, if I remember, about 40 pages or longer, in which he gave a summary of his of his cosmological views. Probably we tried to find out the origin of this paper. It was never published. Probably he was ordered by some Catholic encyclopedia, which was supposed to be published in Japan before the war. Because of the first page of this manuscript, Lemaître wrote Japanese encyclopedia. But then the war started, and probably that paper was never sent to be published, and it remains in unpublished form. But from the philosophical point of view, there are many interesting comments. Some of them are very similar to those published in Solvay conference. But the paper was certainly earlier before the Solvay conference. Okay? And here is only just a few words about his religious views. We discussed that this morning, so I skip that. He said that such a concept of the natural beginning remains entirely outside any metaphysical or religious question. If material is free to deny any transcendental being, and for the believer, it removes any attempt to familiarity with God, as you were already quoted as Anastasia and James Springer. It is consonant to the wording of Isaiah speaking of the things of in the beginning of creation. Something reading. Perhaps we will discuss that tomorrow, so I will show the picture that nowadays observation of the most distant I1, I8 supernova show that that the universe is accelerating. This is the major problems with the origin of the dark matter, dark energy, and so forth. And as when the observational data from supernova accumulate, it is more and more evident that the best fit to this data is the following model. This one. So it starts probably with something which will say that time threshold, which is great question mark here, and then there's acceleration slowing down. This is a quasi-static period, and there are three possibilities: collapse and accelerations. Again, this is a flat version of the model, the most out of favor today. And manipulate. This is with cosmological constant, and with manipulating with the cosmological constant, we can prolong this quasi-static period. And this is the best fit to the present data. And we recognize in that element solution. Is this just by chance that is agreeing with the predictions, or there is some deeper reason? I think that there might be a deeper reason, because Lemaître needed this quasi-static period not only in order to make a concurrence with the long age of the universe, but also he needed that for the processes leading to the formation of galaxies and clusters of galaxies. He needed such a period in which expansion is not disturbing the process of collapsing of matter into some local structures. And he did a lot of work, both numerical and also theoretical, about, in the later part of his life, about this gravitational instability leading to the formation of clusters of galaxies and galaxies. So he needed that period, and it's not impossible that for the same reason we would like to have this constant part of the model. This is the same picture in a different style, with the Big Bang expansion, slowing down, and again acceleration. In 1931, Association for the Advancement of Science a discussion devoted to the evolution of the universe. And all prominent cosmologists of that time, astronomers, were present at that discussion. And in the supplement to Nature, there is a report of that meeting. And at the end of the meeting, James Jeans said the following: suppose some infallible oracle offers to give us yes or no answers to 2 scientific questions for each of us. Personally, I think I might choose as my 2 questions the following. First, does the main energy of stellar radiation come from the annihilation of matter? And the second, is the universe expanding at about the rate indicated by the spectra of the nebula? Well, it's interesting which questions we would formulate. The next speaker was Lord Lemaître. And he said, if I had to ask a question to the infallible oracle alluded to by Sir James Jeans, I think I should choose this. Has the universe ever been at rest, or did the expansion start from the beginning? Is the model from 1927 or 31 correct? But I think I would ask the oracle not to give the answer, in order that the subsequent generation would not be deprived of the pleasure of searching for and of finding the solution. So thank you, Monsignor Lemaître, for your generosity, only to which we have something to research, to investigate. And I think we should also promise our successors not to solve everything, but rather to give something to them, not to claim that we have solved everything. Thank you.
Thank you very much, Michael. Open to questions or comments?
Thank you for that nice talk. There's just one question. You said that Lemaître's 1927 paper was the first one confronting models with the data. I don't think that's correct. Eddington's book of 1924, The Mathematical Theory of Relativity, had data from Slipher about redshifts and distances. And he didn't have the right model, but he did try to compare Slipher's data with cosmological models.
You are right. There were some attempts. To deduce the expansion of the universe from Desitter solution even earlier.
Yeah.
We did not mention this morning, but there was a German astronomer, Wicks, I think it was his name. So he was not absolutely the first one, but I think it was done in a good way, in a correct way.
Sure.
This was, in that sense, he was the first.
You have questions? No.
Okay, concerning the 1933 paper, which was very important, and it's true that it was not translated into English during his lifetime, but it has been translated. About 10 years ago, there came an annotated translation in General Relativity and Cosmology.
Yes. Yes, in fact, I would not. There is a section in General Relativity of gravitation that goes all this, and they translate some better, more important papers. Yeah, thank you.
Yes. Professor Heller, you mentioned Lemaître's lifelong commitment to the view that space must be finite, and you put it under the category of a prejudice or an ideological commitment. I was wondering what kind of question you think it is, whether space is infinite or finite. In what discipline do we search for an answer to that question? Is it a cosmological question or is it a philosophical question?
It's a good question. I would say, perhaps, in the following way, that we would like to have it a cosmological question. But, in fact, it depends how we define cosmological and metaphysical question. Because, you know, let's take as an example our present view that the universe is flat. So we have no vestiges of curvature to the horizon. But we have no guarantee that behind the horizon the universe starts to curve. And this will be, I think, always like that. We can also only broaden our horizons and to say that within our horizon space is flat or within the arrows of our measurements. But the only way to decide that for sure would be if we had only one correct cosmological model in which space would be infinite.
From a cosmological point of view.
But I personally do not like classifying which question belongs to which science. We should be aggressive with respect to science, even if it seems to be a metaphysical and we want to solve it scientifically. We should try to do it. We should be aggressive in science. And, yeah.
But even if you think that it is impossible for cosmology to solve that question, one should be aggressive to try to solve that which is impossible in cosmology? Because that presupposes that we can know that it's impossible.
We should be aggressive always.
Right, well, that's great. I was just curious, did Three Ray Bells write down the k equals +1 model for just pure cosmological constant, no matter, just the de Sitter and the k equals +1 for it's just three spheres that, you know, contract and expand? I mean, then they wouldn't have had problems with, they'd have a closed universe spatially, no singularity anywhere. So I'm curious at what stage that was first written down.
I don't quite understand your question.
Well, it's just the k equals +1 version of de Sitter.
And by de Sitter?
No, de Sitter with positive cosmological constant.
Yeah.
The thing that's a hyperboloid. The thing that the radius goes as a hyperbolic cosine of time.
Yeah.
And that is, I mean, it fit the assumptions of closed spatially, and it's non-singular for all times. So I'm just curious, when was that first written down and understood?
This I don't know when it was the first time written down, but if you look at all the solutions presented by Friedman, there are such models.
Right.
Yeah.
Did he ever consider the limit of zero matter to just a pure cosmological constant?
Friedman did not consider because he had no time, because he died in 1975.
Yeah.
By the way, once I discussed it after a small meeting with some cosmologists, there was Zeldovich was present at that meeting, and I said a lot about the net, because I was returned from Belgium, and I wanted to know something about Friedman, because at that time nobody knew many things about Friedman. He was very persona non grata in Soviet Union, Friedman. His two co-workers, Bronstein and Friedrichsen, was liquidated by some in the 30s. And I asked Zeldovich about Friedman, and he said only that look at the picture, at the photograph of Friedman and Lemaître. Lemaître is a hard man. And he said, and look at Friedman, and you see that Lemaître was never hungry. And Zeldovich said another thing, that Friedman had a chance that he died in 1925. And later on I learned that in the 30s two his collaborators were liquidated. About this is just a remark. It would be a very interesting thing, by the way, to have a conference like that one, devoted not only to Lemaître, but just to kind of comparison between Lemaître and Friedman. They were both parallel and anti-parallel people. They did almost the same. They had great interest in meteorology, both of them. Lemaître because of the cosmic rays, and Friedman was a meteorologist. Both were connected somehow with radiation, and so on and so on. So it would be very interesting.
sure you've got a chapter on it.
Well, yes, so I want to do the chapter.